Alright guys, this video is to answer a couple of questions that inquisitive students often ask about this material. For those students who aren't interested in why the secant substitution is a little bit different, you don't have to watch this video, but this is for those people who are wondering why. Why do I have to do this here when I didn't have to do the same thing for the sine substitution or the tangent substitution? Another question that students often ask is, why do I choose this when x is greater than a, and this when x is less than or equal to a? Or this should be negative a, excuse me. Like, what if x is between negative a and a? All of those are great questions, and they can be explained in a couple of different ways. I'm going to explain them using the graphs of the secant function, the tangent function, the sine and cosine functions, and then we'll also talk about why x shouldn't be between negative a and a for a couple of reasons. So I think probably like the easiest question to answer, we'll answer that first. Question 1. Some students might say, what if x is between negative a and a? So that's a good question. Let's say you've got this example. You've got the square root of x squared minus 9 dx. We actually did a very similar example in the secant substitution video. We've got the x squared minus a squared, so it's a secant sub. And you might say, well, we used the bounds to figure out whether x was less than or equal to negative a or greater than or equal to a. What if our bounds were, say, in this case, a squared is 9, so a is 3. What if our bounds were from negative 3 to 3? Well, obviously we can't plug in 3 or negative 3 because then we'd be dividing by 0. And you might say, well, I'm not worried about those numbers, but what if x was somewhere between negative 2 and 2? And I would say to you, I'm never going to do that to you. And the reason I'm never going to do that to you is those values, those x values, aren't in the domain of this function. Not if this is a real valued function. So let's just think about the domain of this function. The domain of the function tells us why we're never going to have x values between negative a and a. So what we have here is a square root of an x squared minus 9. Even if it wasn't in the denominator, we'd have a square root of x squared minus 9. Let's say that y is equal to that, and we just want to find its domain. Now remember, the domain of this function consists of all the x values where this expression under the radical is positive, because I can take the square root of a positive number, or when the expression under the radical is 0, because I'm allowed to take the square root of 0. Now if x is 0, I have the square root of negative 9, which is 3i, and we're not interested in complex numbers, not at this point in our studies, not in this section. So that x equals 0 turns out to not be in the domain of this. So if I'm trying to find the domain of this, I need to set the expression underneath the radical greater than or equal to 0. Now one way that you can do that is you can say, well, let's solve for x squared. When is x squared greater than or equal to 9? Now you may be tempted to take the square root of both sides and then tell me that x is greater than or equal to plus or minus square root of 3. And that's not going to be 100% correct. It's not going to be exactly right because x isn't just greater than negative 3. It can't be negative 2. That wouldn't work in here. X can't be 0. That wouldn't work in here. So we have to be very careful when we're solving this inequality. Taking the square root of both sides isn't enough to get us the right answer. So there's a different way we can look at this. I might look at this function x squared minus 9 and think about when it's greater than or equal to 0. Geometrically is probably the easiest way to approach this problem. Because we all remember what x squared minus 9 looks like, right? x squared, y equals x squared is just a parabola. It opens up, it starts at the origin, that's its vertex, and it just goes that way. What does that minus 9 do to it? Do you remember? Well, if you don't remember, it's okay. What we are doing is we're going to take all of the old y values, the y values on the y equals x squared graph, and we're going to move them down 9 units. We're subtracting 9 from all the y's. Subtracting 9 from 0 is going to give me negative 9. Subtracting 9 from 1 is going to give me negative 8. Subtracting 9 from 4 is going to give me negative 5. So all of the points on the y equals x squared graph, which were up here, all of those y values are going to get shifted down 9. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Not to scale. My marker is not working anymore. So it's just a parabola shifted down 9 units, and now I've got a graph that looks something like this. Okay, so the question now becomes, well, when is this positive? I need x squared minus 9 to be greater than or equal to 0. Well, it's positive right there and there. It's over here and over here. To figure out what intervals those are, well, we can set y equal to 0. That'll give us those x values. I think we all know the answer to that. Take the square root of both sides. Don't forget your plus or minus. We're going to get x equals plus or minus 3. And we see from our graph that x is going to go from 3 to infinity, or negative infinity to negative 3. Remember, we always read left to right. So the domain of this is negative infinity to negative 3, including negative 3, because it's fine if we take the square root of 0. We're okay with that. Union 3 to infinity. So x can be in this set or this set, and those are all the x values in the domain of this guy. Now this one is a little different. On this one we can't divide by 0, so the endpoints, negative 3 and 3, wouldn't be included. But you can see this is only well defined if x is greater than 3 or less than negative 3. Or, like I've written here, x is greater than or equal to a or less than or equal to negative a. That's when this function is well defined. So that's one way of looking at it. If I pick any x value in here in between negative 3 and 3, if I choose 0, I get the square root of negative 9. Don't want to do that. If I choose 1, I get the square root of negative 8. I don't want to do that. If I choose 3, square root of 0 is fine. If I choose 4, square root of 16 minus 9, square root of 7, it's an irrational number, but that's okay. That's totally fine. So I can plug in any of these x values over here or over here. I just can't plug in the x values in between negative 3 and 3. So those guys aren't in our domain. Our domain includes all of these guys and all of these guys. So this is a great question. You might say, you're leaving something out. What if x is between negative a and a? It's not going to be. And it's not going to be because if this square root of x squared minus a squared is part of our integrand, all the x values between negative a and a are not in the domain of the function. So you're never going to see something like this where x is between negative 2 and 2 and a is 3. It's just not going to happen. But it's an excellent question. Another question that comes up is, why do we have to let the square root of x squared minus a squared equal a times the absolute value of tangent of theta, which is a tangent of theta sometimes when x is greater than or equal to a, and negative a tangent of theta other times when x is less than or equal to negative a. Why do we have to do that when we make a secant substitution? Students say, is that really necessary? And I tell you that it is. And then I say, do this. Whenever your integral has bounds, do this. You say, are you sure I have to do that? And if I have to do it here, Why didn't I have to do that with my sine substitution or my tangent substitution? All excellent questions. First, let's answer this one, and then we'll talk about why we didn't have to do it with our sine substitution or our tangent substitution. To get started, we need to look at the graph of secant of theta. Now remember what secant is. Y equals secant of theta. That's 1 over cosine of theta, right? So if I want to have some sense of what the secant graph looks like, one way that I can figure out what that looks like is I can graph the cosine function and then use that cosine function as a guide to figure out where my secant graph will be. Now remember, cosine starts at its max, and then 1/4 of the period later, it's at 0. And then 1/4 of the period after that, it's at its min. Then it's back to 0, and then it's max. So I'm going from, a regular cosine would go from -1 to 1. If I multiply that cosine by a, it goes from -a to a. So I go max, 0, min, 0, max. Repeat. Max, 0, min, 0, max. Repeat in both directions. And you just keep going. Okay, and remember the period of sine and cosine is 2 pi. So this is pi over 2, and that's pi, and that's 3 pi over 2. And that's 5 pi over 2. And then we get 3 pi. And so you get pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All of the odd multiples of pi over 2, negative pi over 2, negative 3 pi over 2. All of those are where the cosine is 0. And what I've graphed here is the cosine of, or y equals the cosine, or a times cosine of x, or cosine of theta. Now this can be a guide for my secant function. Secant is 1 over that. So anytime this is 0, we're going to have a problem. The secant of theta is not going to be well defined. So I can draw asymptotes there. Remember 1 divided by 0 back in Calc 1. It means we're going to have an infinite limit as we get very close to these lines, so we're going to have some asymptotes. Okay, and then we think about, okay, what happens when I take 1 and I divide it by this number that's always between -1 and 1? Or I divide it by this number that, or if I take, let's multiply this by a. If I take a, which is a positive number, and I divide it by this number between -1 and 1. Well, when theta is 0, we get cosine equal to 1. So a divided by 1 is a, so our secant function is right there. And then as we get closer and closer to pi over 2, cosine is getting very close to 0. We're looking at the y values on this graph. The y's are getting very, very close to 0, but they're still positive, right? So I've got a positive number divided by a tiny positive number, like 1 over 1 millionth. Remember how we divide by fractions? We multiply by the reciprocal. So I flip 1 millionth and I get 1 million. Like, it's going to be huge when I multiply those. So I end up with something that looks like this. The same thing happens on the other side. This is a tiny positive number. A positive constant divided by a tiny positive number is a large positive number. And so we get that. And then over here, cosine was -1. So I've got a divided by -1. So it's -a. And then the cosine is a tiny negative number. A positive divided by a tiny negative is a large negative number. Large in magnitude, but negative sign. Same thing happens on this side. And so we get these U-shapes. They're not parabolas. A lot of students think they're parabolas. They're not. They're not even hyperbolic functions. They're inverse, or they're trig functions. They're secants. That's the graph of secant of theta. Now, whenever we are finding the arcsecant of something, whenever we're defining our inverse trig functions, notice first of all, this doesn't have an inverse. If I were to try to take an inverse to this function, or if I were to try to determine if this function had an inverse function, it would fail. Because remember, in order for a function to have an inverse function, it has to pass the horizontal line test. If I draw a horizontal line here, it crosses there, and there, and there, and there, and there, and there. So this does not have an inverse. But if I restrict it, and this is an arbitrary restriction, but all the mathematicians agree this is what we're going to do. When we say arcsecant, what we mean is take secant, this purple graph that I've drawn for you, and restrict it to negative pi to pi. Then switch the x and y, and that's going to be the arcsecant function. That's exactly what we do. So with this substitution, x equals a secant of theta. If I solve that for theta, by first dividing by a, I get this. And then to get rid of the secant, I take the arcsecant, or the inverse secant of both sides. And remember, those inverse functions, they undo each other. And we're left with this. I get theta equals the arcsecant of x over a. So that's what we're going to get. Now, if theta is the arcsecant of x over a, that means that theta is always going to be some angle in between 0 and pi. It's not going to be pi over 2. You might say, why is it an angle between 0 and pi? Because that was the restriction on the domain that we took in order to come up with the arcsecant in the first place. So we restrict it so that it has an inverse. We say, this original graph did not pass the horizontal line test, but if I just take that piece and that piece, it does. Every horizontal line only crosses that yellow piece once, and every horizontal line down here only crosses that yellow piece once. So this has an inverse, whereas the original secant didn't. So theta is always going to be some number between 0 and pi. And notice the output. If I'm talking about a secant of theta, the x values, those are given by the range of this graph. A secant of theta is given by the y values on this graph. X is always going to start at a, it's going to be equal to a, or be some number greater than a, because a secant of theta always gives me a number that's a or greater than a, or it gives me a number that's negative a or less than a, gives me this piece. We never get any of these numbers in between. That goes with the cosine function. And we took the reciprocal of that, so it's gone. So the x's, the output of a secant of theta, is never between negative a and a. So that's another reason why you're never going to see these bounds that are between negative a and a up here. But back to what we were talking about. This purple function is the secant function. If I take the restriction so that the arcsecant exists, I'm just talking about this one little part. This part and this part of the secant function. And then we're going to switch to x and y, and we're going to call that the arcsecant. Okay, you might say, what on earth does that have to do with anything? What does that have to do with this? Well, let's talk about the tangent graph now. This is what secant looks like. Tangent looks like this. It's sine of theta over cosine of theta. And if I multiply by a, it's just stretched a bit. It's just a times is tall. I take the old tangent values and I multiply them all by a. So the tangent graph is going to look like this. Now this is undefined when cosine is 0, just like this one was undefined when cosine is 0. So the asymptotes are exactly the same. But tangent looks like this. It's 0 whenever sine is 0. And sine is 0 at all of the multiples of pi. And then it has this beautiful shape. And hopefully back in Calc 1, or maybe even in Trig, Someone talked about limits with you and talked about how we get this beautiful shape. Infinitely many branches. Just looks like that. Okay? Okay, you say, what on earth does that have to do with this? Well, okay. First of all, just because of algebra, we know the square root of x squared minus a squared was the square root of a squared, which is a because a is always positive, times the square root of tangent squared. And the square root of something squared is always the absolute value of what you started with. If that number is positive, I don't need the absolute value bars. But if that number is positive sometimes and negative other times, I need the absolute value because this is only going to give me a positive number back. We claim that whenever we do a secant substitution, the absolute value of tangent of theta is going to be tangent of theta. It's going to be positive whenever x is greater than a. And let's check that out. If x is greater than a, that means a secant of theta is greater than a. So we're right here. We're on this yellow branch. Is tangent of theta positive there? Looking at the y values, yes. On that branch, tangent of theta is certainly positive. So we're good to go. As long as x is greater than a, tangent of theta is positive or possibly 0. And then we're right here. So a times the absolute value of tangent of theta is positive, and I'm just going to write that down whenever x is greater than or equal to a. Now, if x is less than or equal to negative a, that means I'm over here. Question is, on that piece, when we're here, is tangent positive or is tangent negative? Look at the y values, guys. We're talking about that. Those y values are negative. They're below the x-axis. So if I want the absolute value of a negative number, like if I want the absolute value of negative 2, I've got to multiply it by negative 1. Negative 2 times negative 1 would make it positive 2, right? I take my negative number and I multiply it by negative 1 to make it positive. So when x is less than or equal to negative a, we're down here, and in that case, tangent values are negative, and if tangent values are negative, its absolute value is that number times negative 1. And I know that's still hard for a lot of students to understand. Here's one way that you can think about it. Let's just ignore the trig functions for a minute. You remember this absolute value graph from pre-calc, right? Someone probably also told you it's just going to give you x when x is greater than or equal to 0. Isn't that right? Absolute value of a positive number, isn't that just the number? Absolute value of 3 is 3. Absolute value of 10 is 10. Absolute value of 5 is 5. Absolute value of a million? A million. Absolute value of 0? That's a distance of 0 from 0. 0, that's fine. So this is going to work out just fine. But if x is negative, y equals x looks like this. So when x is negative 2, y is negative 2. When x is negative 3, y is negative 3. I'm going to take the absolute value of that, though. So I'm going to take all these negative y values and I'm going to multiply them by negative 1. That's going to flip this whole part up, and it gives us that V shape. That was x, and I multiplied it by negative 1. Now it's negative x. And that's when x is less than 0. A lot of students have a really hard time with that because they say, that looks negative, it doesn't look positive. I thought the absolute value was supposed to give me a positive number, but it does, because this is a negative times a negative. And a negative number times a negative number is that positive number. It's that absolute value. So here, when we're on this branch, when we're on this part, when x is less than negative a, we're on this part of our secant graph. The tangent is right here. Tangent of theta is there, and tangent is negative there. So if I want the absolute value of that negative number, I multiply it by negative 1, makes it positive. So that's what we get there. Okay, third excellent question. if I had to do this for this, why didn't I have to do it for the sine function or the cosine function? And the reasoning is very similar to what we just went through, but it's actually very easy to see. Okay, on this one I've already drawn the graph. All right, so for our sine substitution, our sine wave looks like this. We know it repeats every 2 pi, and it repeats, and it repeats, and it repeats, right? It keeps doing this thing. So we're here. Now, when I solve for theta, first I have to divide by a, and then I have to take the inverse sine, or the arc sine of both sides. In order for that to work, in order for us to even have an inverse function, well, that means that my theta values have to be between negative pi over 2 and pi over 2. We had to take some restriction of this so that we could find an inverse function. And I don't know the history, but mathematicians agreed somewhere along the line that we were going to take this restriction, the one from negative pi over 2 to pi over 2. So as long as we're on this restriction, notice the graph passes the horizontal line test. You say it doesn't pass over there. You're right. That's why we had to restrict it. But if I'm just restricting myself to this little yellow piece, now this passes the horizontal line test. And since it passes the horizontal line test, I can find the arc sine of that. I'm going to get a different, or I can get theta by itself and have an inverse function. Sine has an inverse function as long as I restrict it to that interval. Okay, so now we're on the interval from negative pi over 2 to pi over 2. We've restricted ourselves in that way whenever we've decided that we want to be able to solve for theta. And we want to be able to solve for theta in these trig substitution problems. Okay, so we're on the interval from negative pi over 2 to pi over 2. And we simplify the square root of a squared minus x squared. That was what started all of this. It looked like an arcsine integral. It wasn't an arcsine integral. It wasn't a u sub. But since it looked like one, we were going to make a sine substitution. When we make a sine substitution, this reduces to this. And square root of a squared is a. And square root of cosine squared is the absolute value of cosine. I told you earlier that it was equal to a cosine of theta. You might say, yeah, Miss Townsend, did you lie to me? Are you telling a little fib? Like, is that really not equal to, is this really equal to this all the time? It's not always equal to that, but it is equal to that for the theta on this interval. And let me show you why. Here's the cosine graph. It repeats every 2 pi. If I'm assuming that theta is on the interval from negative pi over 2 to pi over 2, I'm assuming I'm right here. Aren't those cosine values already positive? So there's no need for the absolute value bars. Here, since my cosine's already positive, the square root of cosine squared is cosine. And you don't have to worry about that. Tangent is similar. When we make the tangent substitution, well, this is what we're dealing with. We've got a tangent function. It's got that beautiful graph. It repeats and it repeats and it repeats infinitely many times in all directions. It's quite lovely. But just like before, we got a problem. It fails the horizontal line test. So when I solve for theta, by dividing by a and taking the arctangent of both sides, I can do that, but I have to be sure. When I do that, I'm assuming that that theta is between negative pi over 2 and pi over 2. When someone in history defined these inverse trig functions, they said, okay, when we're talking about the arctangent, we're talking about this part of it. We're not talking about that part. We could have taken that part. We could have just as easily taken that one or another one, but we chose, and then we stuck to the convention that theta was going to be between negative pi over 2 and pi over 2. We're going to take this restriction, switch x and y, and that's going to be our arctangent graph. Excuse me. I say, okay, well, what on earth does that have to do with us and with our trig sub? Well, it doesn't have anything to do with it in this case, and I wanted to show you why. The square root of x squared plus a squared, after doing your substitution and factoring out the a squared and using your Pythagorean identities, you got tangent squared plus 1 was secant squared. And that is, by definition, a times the absolute value of secant. But I told you that it was this. And it turns out that it is. It's that all the time. You say, why? Well, if I'm on the interval from negative pi over 2 to pi over 2, so my theta values are in here, well then, I'm on this branch of the secant graph. Those secant values are already positive. They're already greater than or equal to a. So secant is positive here, so I don't need the absolute value. Sine is positive here, so I don't need the absolute value. I don't need the absolute value when I make a tangent substitution because of this, and when I make a sine substitution because of this. When I make that sine substitution, there is an assumed restriction on theta. And based on that assumed restriction on theta, this is going to be equal to a times cosine of theta, because cosine of theta is positive. And based on the assumed restriction on theta here, this is going to be equal to a times secant of theta, and secant of theta is positive. Now let's go back to that secant substitution. With our secant substitution, x equals a secant of theta, it's not as clear. When I solve for theta, if theta equals the arcsecant of x over a, we're here. Theta has to be between 0 and pi over 2, or pi over 2 and pi. And that's fine. I mean, that's a totally fine restriction of the secant function so that we can have an inverse secant function or an arcsecant function. But then in that case, if I've got the square root of x squared minus a squared, which we said was making a secant substitution, x squared minus a squared is that. And if I square both of the factors there, I get that. And if I factor out the a, I get that. And then I see my Pythagorean identity and I get excited because things are good. Things are getting simple and clear and nice. Isn't that nice? Square root of a squared is a because we assumed a was positive. And the square root of something squared is its absolute value. But we're not as lucky this time as we were down here. On this restriction, when theta is between negative pi over 2 and pi over 2, cosine is positive. When theta is between negative pi over 2 and pi over 2 here, secant is positive. But what happens here? When theta is between 0 and pi over 2, tangent is positive. So we're good to go. This is tangent, or a tangent of theta, because the absolute value of tangent is tangent when theta is between 0 and pi over 2. And when theta is between 0 and pi over 2, that means x is greater than or equal to a. I guess it could be equal to 0. But what happens on the other interval when theta is between pi over 2 and pi? Or when x is negative a, or less than negative a? Well, in that case, my tangent function is negative. The y values on the tangent graph, they're below the x-axis, so the y's are all negative down here. And if the y's are negative, if I want to make them positive, take the absolute value, I need to multiply them by negative 1. So I'm taking a tangent of theta, which is negative in this case, and I multiply it by negative 1. Negative times a negative is a positive, and that's giving me that positive a times the absolute value of tangent of theta. So that's why we have to do it. That's why we have to be careful with the secant substitution, where we didn't have to be so careful with the sine sub or the tangent sub. I know this is a long video, and it's not necessary in order to use the substitutions to solve the problems, But for those curious students who really wanted to know why we do everything differently for the secant sub as opposed to this tangent sub and the sine sub, I wanted to make this for you. And also, I wanted you to know, when we have this special case, x is greater than or equal to a, or x is less than or equal to negative a, we're not leaving out all those a values between negative a and a. X can't be one of those a values. If x is a secant of theta, well, x isn't in between here. There is no secant graph in between negative a and a. So x can't be there. Or another way to look at it, this function's not well defined when x is between negative 3 and 3, or if that was an a squared between negative a and a. We're going to get a negative under the radical, and we don't want that. Not in calculus involving real variables like we're studying in this class. So that's that. Thanks for listening.